Okay, this video is going to be about nuclear physics, and earlier in the notes we said that the nucleus was discovered by Rutherford in his gold foil experiment, and he found that the atom was mostly empty space with a tiny, dense, positive nucleus. Now, it was later found out that the nucleus was made up of protons and neutrons. And if I was to look at a nucleus, it might look something like this. I'd have a proton here, and maybe a proton here, and a neutron there, and another neutron. That would be a helium nucleus with 2 protons. But if you look at it like that, you may come up with this question: why don't the protons repel each other and fly apart? Okay, how can a nucleus exist at all? And they came up with this idea that there is a strong force its properties are that it is strong enough to overcome the electrical repulsion of the protons but it also only works over a very short range. Like 10 to the minus 15th meters. Because once a proton gets a little bit more than 10 to the minus 15th meters outside the nucleus, then it is going to repel. It actually sets an upper limit on the size of our nuclei. The naturally forming nuclei, if we look at the periodic table, the largest ones have about 100 protons. Once they get bigger than that, the nucleus itself is getting bigger than that 10 to the minus 15th range, and the nucleus flies apart. Now, there are 4 fundamental forces, and so we'll start with the strong force, and the extent of it is very short. It works on things in the nucleus, so nucleons. That just means protons and neutrons. And it holds the nucleus together. And we're going to rank these from strongest to weakest. The next one is the electromagnetic force. Its extent is infinite. It gets weaker and weaker the farther apart things get, but it never stops. It works on charged particles, so charges. It can attract or repel. The next one is called the weak nuclear force, and its extent is very short. It works on things in the nucleus as well. And you don't really know much about it other than it exists. It takes part in nuclear decay. And then the weakest of the 4 forces is gravity, gravitational. It is also infinite in extent. It works on anything with mass, and it only attracts. Now, it may seem weird to say that gravity is the weakest of the forces, but you have to have gigantic masses, like the mass of the Earth and the mass of the Sun, to even feel a gravitational force. I certainly don't feel a gravitational force, say, between me and a desk. It turns out these are the fundamental forces. All forces really are made up of these forces. For instance, the normal force between my feet and the floor is really an electrical repulsion between the electrons in the floor and the electrons in my feet. Mass defect. When scientists started studying nuclear reactions, they found that mass was not conserved. And probably at first they thought they were making a big mistake. Like, one of the most fundamental laws in chemistry is that mass has to be conserved. But they always found out that the mass wasn't. Okay, the mass of the products might be a little bit less than the mass of the reactants. So what was going on? So they called the mass that they were missing a mass defect. A defect is a problem. So missing mass is the mass defect. And they determined that the mass is turned to energy. And you can find out how much energy by using the famous equation E equals mc squared. Mass is mass in kilograms, energy is going to be in joules, and c is the speed of light. Which we remember is 3 times 10 to the 8th meters per second. So our first example here is going to be that if we could completely destroy 1 kilogram of matter, how much energy would we get out? So E equals mc squared, 1 kilogram, times 3 times 10 to the 8th squared, and that's 9 times 10 to the 16th joules of energy. So that's a lot of energy. Antimatter. Okay, every particle has an associated antiparticle. With the same mass and opposite charge. All right, and when matter and antimatter meet, they annihilate. Each other, which means all of the mass turns into energy. So they are completely gone and turned into energy. So here's an example of how much energy is created if a proton and an antiproton touch. So a proton has a mass of 1.67 times 10 to the minus 27th kilograms. And an antiproton is going to have a mass of 1.67 times 10 to the minus 27th kilograms, because the mass is the same. The only difference is the antiproton would be negative. I'll put that little line over it to show that it's an anti. So the total mass I can get by just adding those together, or doubling the mass of a proton, and I get 3.34 times 10 to the minus 27th kilograms. Then to find out how much energy I get from that, E equals mc squared, 3.34 times 10 to the minus 27th times 3 times 10 to the 8th squared, and I get a value of 3.006 times 10 to the minus 10th joules. Okay, so for just one proton and antiproton, it's not a whole lot of energy. So one thing that's really kind of cool is this can happen in reverse. Instead of the two particles touching and turning in energy, you can have energy spontaneously turn into matter. And it's called pair production because it's always a pair of particles. So we have this question, how much energy is necessary to create an electron-positron pair? A positron is the name for an anti-electron because it's an electron except with a positive charge. So if I was to sketch this, you'd have this energy, and then suddenly an electron and a positron would appear. And it's going to be almost, it's like the other problem in reverse. Okay, the mass of an electron is 9.11 times 10 to the minus 31st. The mass of the positron is going to be the same. So the total energy, the total mass that gets destroyed is 1.822 times 10 to the minus 30th kilograms. And then E equals mc squared, 1.822 times 10 to the minus 30th times 3 times 10 to the 8th squared. And I get an energy of 2.02 times 10 to the minus 1.64 times 10 to the minus 13th joules.